I'm going to tell you about my collaboration's efforts to explore the environment around galaxies and coupling the very earliest galaxies to the Milky Way. And I could not have done this without my extensive list of collaborators and a variety of allocations on Blue Waters. So what are the questions that we're trying to answer fundamentally? So first off, we're trying to address the earliest progenitors of the Milky Way, and we'll talk about that in just a second. But basically, the Milky Way was formed by the merging of many, many generations of previous galaxies, and we're very interested in the first ones and how they grew and how they set the stage for later generations of structure formation. We also want to know how to connect those very first galaxies to the local group, and we also want to know how the galaxies, like the Milky Way, interact with their environments and how they regulate themselves, because galaxies in some ways display remarkably interesting and constant properties, or at least predictable properties. So our motivations fundamentally come down to the idea of hierarchical structure formation. And here we go. So this is on the left, you have an observational image of a bunch of galaxies that are interacting with each other. And on the right, we have a simulation, not done on Blue Waters, of a bunch of dark matter halos that should contain galaxies that are all merging together over many billions of years. And fundamentally, this is how cosmological structure grows in the universe. Galaxies get built by small objects forming early in time and merging to make successively larger and larger things. And that has some really interesting implications if you are trying to study how galaxies evolve over the universe. First off, observationally, when we look at something like this, which is the Hubble Deep Field, one of the deeper images of the night sky that was ever taken, though this is becoming less and less true, what you see is lots of really interesting behavior. You see that there are lots of evidence of galaxies merging. Here are some pictures of a bunch of those galaxy mergers. And when you look at the highest redshift, which is to say the most distant objects, you see that they're very different than galaxies you see at the present day. And so this picture, this image, really a mosaic, paints the picture of galaxy formation as things growing over time. And so it also tells us that there are lots of galaxies like the Milky Way, and those galaxies often have many, many satellites around them. And hierarchical structure formation, the theory of hierarchical structure formation, tells us some really interesting things about those satellites. So first off, when something like the Dark Energy Survey goes out and looks, we see tons and tons of little dwarf galaxy satellites around the Milky Way. These three here happen to be small, ultra-faint dwarfs. They are very small and they're very dim, hence the name. And they are really, really interesting because they are relics of those very earliest epochs of galaxy formation. And so what that means is that those pictures of the most distant galaxies that you can find in the Hubble Deep Field, you can connect them directly to galaxies that are in our own cosmic neighborhood. Also, quite honestly, I'm interested in this to make predictions for two telescopes. One of them is the James Webb Space Telescope, which is going to be launched approximately 2 years from now, barring any unforeseen delays. And then the other is the Large Synoptic Survey Telescope, which has some strong ties to NCSA. The first light for that is going to be next year, and the first science results are going to be a couple years after. And both of these machines are going to completely revolutionize our understanding of the universe. The James Webb Space Telescope is going to look deeper into the past and find galaxies that we could not possibly have seen before. And LSST is going to collect tons and tons of light, and it's going to find lots and lots of those ultra-faint dwarf galaxies. So when we do this work on Blue Waters, we use two fundamental tools. And so the first thing that we use is ENSO. There's a lot of text there, I apologize, but basically it's an adaptive mesh refinement code. You've all heard of those. It has all sorts of physics that you would care about if you were doing galaxy formation. And also we do a lot of our data analysis, which is mostly what we spend our time doing, with YT, which is a community-developed data analysis and visualization tool, which is led by NCSA's own Matt Turk. So, okay, what I want to do now is tell you about a few of our recent Blue Waters related results. And so the first thing, so I'm going to talk about the early universe, and then I'm going to talk about the present day. So the first thing is, I am really interested in understanding how black holes formed in the universe. When we go out and we look at galaxies, we see that supermassive black holes, which is to say black holes with masses of millions to billions of times the mass of our own sun, are ubiquitous in the centers of massive galaxies. So the Milky Way has one, Andromeda has one. Any big galaxy you choose to look at has one of these supermassive black holes. And where do they come from? And fundamentally, there are two sort of popular scenarios. That they come from stars in the very early universe that collapsed into black holes. Massive stars do that. And then another theory is that you have the direct collapse of lots and lots of gas into a massive black hole. And both of these have problems. The stellar mass black hole, the problem with the stellar mass black hole theory is that it's very hard to get black holes to grow fast enough to be billions of solar masses by the time that we observe them in the universe, which is about a billion years after the Big Bang. With the second one, this direct collapse scenario, you avoid that growth problem by starting them out a few orders of magnitude bigger, and then they grow. But the problem with that then fundamentally becomes you have to come up with a mechanism to keep gas from forming stars long enough to form a massive black hole. And it turns out that gas desperately wants to turn itself into stars because it wants to cool off and gravity pulls things together and so on. Anyway, so what we did here was actually go back to simulations called the Renaissance simulations, which Mike Norman and I did along with some of our collaborators several years ago with our very earliest PRAC, actually. So this is simulations that we did, I think, 6 years ago at this point, and we're continuing to get results from them, which is an interesting point about the long tail of results that are coming from blue waters. And so these simulations are simulations of sort of order 1,000 galaxies in the high redshift universe at incredibly high spatial and mass resolution with all the physics you could want, including radiation transport and prescriptions for the primordial star formation and feedback and metal-enriched star formation and feedback and so on and so forth. And oops, getting ahead of myself a little bit here. And so what we did in these simulations was we found all of the POP3 stars, these primordial stars that are likely to be the seeds of massive black holes, and we traced them throughout the entire simulation and tried to estimate the growth rate of those black holes as we go through. And this is something that people have been able to do in individual galaxies and simulations, but not in huge populations of galaxies. And so what we're trying to do is see what the average black hole in a galaxy does to grow. And then in a separate project, we went through the same set of simulations where we had thousands of galaxies to prospect through and looked for collapse candidates for the formation of these supermassive black holes. So this first project, where we were trying to estimate the accretion rate of black holes, well, so this is the key figure. And so let me just take a minute to explain this. I'm noticing there's a lot of feedback when you step underneath the speaker there. Anyway, so this is a distribution function of the accretion rates that we find. So the x-axis, so this is just a fractional distribution function or differential distribution function. On the x-axis is the black hole accretion rate relative to something called the Eddington accretion rate. And this is the nominal maximum possible growth rate of a black hole. And in order to take a stellar mass black hole and turn it into a supermassive black hole, it has to accrete pretty much on this side of this plot for the entire duration of its lifetime. And you should read this plot as being, where do black holes spend their time for their first several hundred million years? Well, you can see that it is not over by where I'm drawing this line with my laser pointer. And so on average, these black holes grow very, very slowly, and it takes them an incredibly long time to double their mass. And this is just the cumulative version of that. And then we did some more detailed simulations following this at very high spatial or very high temporal resolution, and these black holes grow at a rate of something like 10 to the minus 12 solar masses a year, which does not get you to billions of solar masses in 10 to the 9 years or something like that. And so basically what we find is that stellar mass black holes simply don't grow very quickly in the early universe, and at least in the average galaxy. And one of the reasons for this is that these stars are massive and bright, and they produce a lot of light. And when you have the supernova go off, plus all this radiation, it's really easy to push much of the gas out of these galaxies. And when you push the gas out, the black hole has nothing to accrete, and it has nothing to feed on and grow. And so this becomes really problematic in terms of scenarios where you make these black holes grow rapidly. They're also very unlikely to merge with each other. Okay, but we also found a new mechanism because we went through these simulations and we looked around for interesting and weird galaxies where there might be a situation where we could keep a lot of gas around without forming stars. And as I said, gas in galaxies wants to form stars. Gravity pulls gas together. Atomic physics allows it to cool off. And once it's getting pulled together and cooling off, then you get stars. And so you need to either figure out a way to keep the gas from cooling or keep it from falling together to form stars. And we went around and looked for that, and we found a couple interesting candidates. And so this is a simulation, or this is an image from one of our simulations. So time goes from left to right. We're looking at two different halos here. There's a tiny arrow, which I'll highlight in just a minute. But this red stuff is a radiation field, and this purple stuff is metal, which is to say everything produced by supernova, all the elements heavier than helium, which enrages chemists, by the way. But the point is that there is this radiation field that is extremely strong that goes out and irradiates lots of the halos in this simulation. And so let me just zoom in here. And you can see there's this halo in each of these circumstances that is an interesting one. And very quickly, these things get overtaken by radiation, but they don't get polluted by metals. And so the radiation is ultraviolet radiation from stellar populations, and metals are also, and so the radiation keeps the gas from collapsing. Metals, you don't want any metals near these halos because the metals help the gas cool off. And so basically, they're in this kind of Goldilocks zone, which is pretty rare in the universe. We only found a couple galaxies in our entire suite of thousands of galaxies that have this circumstance where radiation has kept them from collapsing and forming stars, and they also have not been polluted so that they can form stars. And also, near the end of their lives, they grow really, really quickly. And so what we find, so these blue, so let's focus at the top here. The two solid lines are our two halos, one of which is the one that's the most irradiated, and the other solid line is the one that is the most massive in the box. You see they grow slowly, 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 and sort of this dashed line is roughly where you expect the radiation. The minimum, any mass below that, the radiation is keeping the stars from forming. But then near the end, they suddenly start growing very quickly just because of the environment they're in. And then in that merging together, that hierarchical structure formation, keeps the gas heated. So it actually doesn't, the gas is radiating energy away like mad, but the mergers and all that kinetic energy is getting turned into heat and keeping the gas from collapsing until it reaches this dotted line, whereupon it's essentially gotten to the point where no matter what you do, you can't stop the gas from collapsing. And we get around 100,000 solar masses of gas in a really tiny region of space that, well, quite frankly, that's where the physics breaks down in the simulations, but we could plausibly form the seeds of a supermassive black hole, which we can then form, which we can then follow in later simulations. Unfortunately, again, that's where the physics in the simulations break down, but it is intriguing and possibly something we can follow up on later. Okay, now we're something completely different. Our new project is probing circumgalactic gas in galaxies like our own Milky Way. So this is the Milky Way. This is probably what you think of when you think of the word galaxy, if you're not an astrophysicist. And so we live somewhere over here, but that's not really the point. So this is what we think about when we think about galaxies. When a theoretical astrophysicist thinks about galaxies, here's what we think about. The actual part with the stars is a pretty small part of the whole galaxy. A galaxy like the Milky Way is surrounded by an enormous dark matter halo, which has most of the mass of the galaxy in it. And in that dark matter halo, about half of all the baryons, which is to say all the stuff on the periodic table that you make stars and gas and so on out of, is out here in this circumgalactic medium, out in the dark matter halo. And we have, in general, thought that that gas was essentially the temperature you would expect from gravity pulling it in, which in the case of the Milky Way is maybe 1,000,000 degrees Kelvin. What we have found is that actually galaxies like the Milky Way are full of these little cold blobs of gas that are 100 times colder and around 100 times denser. And as a matter of fact, about half of all of the mass out in this halo, which is most of the mass of baryons in the entire galaxy, including all the stars, so it dominates over the stars, is in this cold phase. And it's very interesting because how did it get there and where is it going and all that good stuff. And so it turns out that it's quite hard to see this. And so the way that we look for it is we find a very bright background source. This is a star, but in reality, it's a supermassive black hole called a quasar that is very far away and accreting material really fast and producing lots of radiation. Then we put the Hubble Space Telescope on the other side, and we wait for radiation to come to it, and we see absorption from when the photons that are coming from this quasar come and hit one of these cold blobs of gas, and we can see all sorts of really cool stuff. And so this kind of quasar absorption spectroscopy, is what it's called technically, tells us that this is true, that these galaxies are all surrounded by these tremendous halos of gas, and that some of it is cold and dense and some of it is hot and diffuse. And a sort of cartoon impression of it would be something like this, where that little disk bit that I showed you is in here, gas is flowing out, gas is accreting in, it's a tremendous mess, it's really complicated, it's really awesome. So, very interesting environment. And so we wanted to go simulate this. And so here is what a typical cosmological simulation looks like. On the left here, we have the spatial resolution of our adaptive mesh simulations. So in our simulations, we use adaptive mesh like many other people do. We put better spatial resolution. The common practice is to put additional spatial resolution as the density goes up. And so here you can see the gas metallicity, just sort of all the ejecta from the stars, but the density generally goes up towards the center, and you can see that the resolution goes up towards the center. But there are really good physical reasons to think that all sorts of interesting stuff should be happening out here where the gas is poorly resolved, and where the spatial resolution is not very good. For example, there's a thing called a thermal instability, which happens in the interstellar medium, which you would also expect to happen out here. And so what we can do when we have a computer like Blue Waters, which has tons of CPU power and lots of memory, is to say, heck with it. I'm not going to let the resolution just follow the mass. I am just going to force the whole thing to be extremely well resolved. And so we did. We forced the entire thing out to, well, in this case, about 60 kiloparsecs, well, 100 kiloparsec cube, to be resolved at much, much, much higher spatial resolution than people typically do in these simulations. And this has two interesting consequences. So first off, we see all sorts of cool stuff, which I'm about to show you. But we also get much better mass resolution, right? Because if the density stays the same and the cells get way smaller, the mass gets better. So the point is, here are dashed lines that represent lots of our competitors. All of these colored particles represent, cells in our simulation, and this is from our original calculation, sort of the standard way that we do these things. And these are, reasonably good simulations. However, when we go to Blue Waters and turn it up to 11, here is what our mass resolution is. We are resolving down to the mass to hundreds of solar masses, or even below that, out in this circumgalactic region. And this is impossible to do without this type of code and without access to a machine like Blue Waters. And we see some really startling differences. So the first thing I'm going to do is just show you a simulation where we take the same set of initial conditions. We start it with the way that we typically do the cosmological simulations, and that's down here. And then up here, we force the resolution to be at this high level of a couple hundred parsecs everywhere. And so just take a look at, pick your field of choice, density or temperature or metallicity, and just look at the difference. I appreciate the sound effects from the audience. So I'm not above doing that myself, by the way. Anyway, so there's all sorts of really interesting stuff that's happening. And to me, what is most striking is that, in terms of bulk behavior, the same galaxy is forming and the big stuff that's going on is kind of the same. But you see so much more structure in the phase diagram, so in the density and temperature, in the metallicity, all sorts of stuff like that. And when we and this has a huge impact on observable properties. So this is the neutral hydrogen around one of these galaxies. And what we can do is shoot a ray through this. I was talking about quasar absorption lines earlier. And this is what we see. So this is one of these high resolution ones. So it's density, temperature, metallicity. This is the H1, so the neutral hydrogen, and then a bunch of different metal lines. And so if we did this in a standard galaxy, you'd see almost none of this structure either in the actual gas properties up here or in the synthetic observations down here, which is quite remarkable. Okay, let me summarize. So first off, stellar mass black holes, from our first results, we find that stellar mass black holes grow very slowly in the early universe. The H2 regions and the supernovae remove lots of gas. It makes it very hard for them to be plausible candidates for supermassive black hole formation based on our radiation hydrodynamical simulations. When we go back and mine our earliest simulations from our earliest Blue Waters project, we did find some really interesting new mechanisms for direct collapse to supermassive black holes, which requires halos that are bathed in a combination of lots of ultraviolet radiation and also very, very rapid growth. And then in our more current project, what we found is that when we increase this spatial resolution and do these very expensive simulations that you can really only do on a computer like Blue Waters, we find that increasing the spatial resolution provides all sorts of really fascinating new observable properties of our simulations, which brings them into much better alignment with the observations and shows all sorts of really cool stuff going on in this circumgalactic gas. And then we also have a third PRAC that we're trying to connect all these things together, but we just started running the simulations, so stay tuned next year. Thank you very much.